Welcome to Pomodoro Joe for January 25th, 2023. Today we're looking at LeetCode problem 2359. Find closest node to given two nodes. This is a medium problem. And the problem statement says, you are given a directed graph of n nodes numbered from 0 to n minus 1, where each node has at most one outgoing edge. The graph is represented with a given zero-indexed array edges of size n, indicating that there is a directed edge from node I to node at edges index I. If there is no outgoing edge from I, then edges at index I will equal -1. You are also given two integers, node 1 and node 2. Return the index of the node that can be reached from both node 1 and node 2, such that the maximum between the distance from node 1 to that node and from node 2 to that node is minimized. If there are multiple answers, return the node with the smallest index. And if no possible answer exists, return -1. Note that edges may contain cycles. Okay, and there's an example here. We have a graph and it says the output is 2 because the distance from node 0, so the input nodes are 0 and 1. Distance from node 0 to 2 is 1, and the distance from node 1 to 2 is 1. Okay, so basically what this comes down to is we have to find shared nodes that are reachable from both node 1 and node 2. We have to find the maximum distances between node 1 and that node and node 2 and that node. And then we want to find the minimum of those maximum distances, or the node that has the minimum distance of those maximum distances. Oh, that's confusing. All right, well, let's set 25 minutes on our Pomodoro timer here and see what we can do. So we'll start with the result, set it to -1, and we'll return our result at the end. Now I think what I need here is I need to traverse these graphs. I need to find all the nodes that are connected to node 1. I need to find all the nodes that are connected to node 2. And keep track of their distances. Once I have this pool of nodes, I can find the intersection of all the nodes that are connected to node 1 and all the nodes are connected to node 2. That'll give me this set of shared nodes. Once I have the set of shared nodes, I just have to find the ones with the minimum maximum distance. Okay, well, let's see what we can do here. So I'll start by traversing the graphs and getting the distances. So I'll have some distance map. And that's going to be a dictionary where the key will be the node and the value will be the distance to, I guess I'll need two of these. So I'll need a distance map for node 1. So in this case, this will be distance to node 1. And then I'll need one for node 2. So again, the map will have a key will be the node, and the value will be the distance to, depending on which map we're in, it'll be either distance to node 1 or distance to node 2. So we'll initialize these with, this one will have node 1, and it has a distance of 0, because node 1 has a distance of 0 to itself, and node 2 also with a distance of 0. So that should be node 2, and that's node 1. Okay, then how do I find these distances? Well, I pretty much have to traverse the graphs. So I'll have some node 1, and that's going to be equal to node 1 to start with. And I'll have some distance 1, that'll be equal to 0. And then I'll have to say, I could do a for loop, but I think what I really want to do is just say, while my distance at index 1 is less than, I guess, the length of my dist map 1. So essentially, if we get to a point where we don't add a node into the map, it means I want to detect cycles, basically. If we find a cycle, we won't add that node into our map because it's already in the map. So our distance will lag behind the number of keys in our map, and that will break out of this while loop. Okay, so while our D1 is less than the length of our distance map at 1, let's see, our new node will be equal to our edges from, so this is basically saying the next node in our list will be the connected node to our current node. And then we'll have to increase our distance by 1. And then we can put our distance map at 1 for this node 1 is equal to our distance. Okay, I think that works, except I need to make sure that we don't have cycles. So we only want to set the value in our map if we don't already have this value in the map. So if n1 not in dist map 1. Okay, so that'll help us break out of any cycles. The other thing it did mention though, it said if there is no connection, yeah, if there is no outgoing edge from this node, then edges at I will be equal to -1. So let's also break out if our node is equal to -1. So this should build up our map. And let's do the same for map 2. Oh, I guess I also need these guys. Now, if I were writing this for production code, I would probably break this out into a function that would do this so I don't have to repeat the code. But since we're just doing this here for LeetCode, let's just do some copy paste for now. All right. So again, this is just going through, following the edges, and building up a map that maps the node to its distance from the respective start node. Okay, now that we've got these built up, let's print these out. Let's just do a quick test here, make sure that we're not breaking anything. It looks like we're building up our list pretty nicely. So distance from 0 to 0 is 0, which, yep, node 1 and 0 to start with. Okay, yeah, this is looking pretty good. Cool. So we can get rid of our prints. All right, so next up, now that we've built up these are essentially our graphs. These are the lists of nodes that have connections to either node 1 or node 2. Now we actually want to find the intersection of these two. So let's see. Let's build, I'll call it graph 1, and it's going to be a set of our dist mapping, our dist map 1. And we just need the keys. So I'll grab the keys out of there. So that's going to just be the node names themselves, or the node values, I should say. And we'll do the same for graph 2. So now graph 1 and graph 2 are sets that just have the node values. We've dropped the distances for the time being. And now I want to find the shared nodes. And that's going to be graph 1 intersection of graph 2. And I'm going to print that as well. Make sure that these are going all right. So this is set operations where we're finding the intersection between two sets. Hey, that worked pretty well. So now we're saying that both graph 1 and graph 2 are connected to node 2 and node 3. And that looks like that is the case here. Cool. And now the final piece, finding the minimum maximums. Okay, so I'm going to have the min max distance, and I'll set it to something really big to start with. So we'll set it to infinite to begin with. So we need to keep track of which one of these nodes has the minimum maximum. So that's it. We need to find the maximum values, and then we have to find the minimum of those maximums. I know it's confusing. So this is going to keep track of the minimum maximum distance we've found so far. And it starts as infinite. And now we just have to go through all of our nodes for node in our shared nodes. All right, so now we have some distances. So we can find distance 1, and that's going to be equal to dist map 1 at this node. And we have d2, and that's equal to dist map 2 at this node. Now, I don't really need these temporary variables, but I'm just doing it to make it clear what we're doing here. So now we want to find the max dist. That's going to be the maximum of those two. So the distance to node 1 and the distance to node 2 from this node. That's our max dist. Let's see, not mad, max dist. Now, if this maximum distance is less than our current min-max distance, well, then we can set our new min-max distance equal to this max distance. And our result, the node, is going to be equal to this node. So that takes care of if it's less than. What if it's the same? Well, they did say over here something about if they're the same, if there are multiple answers, return the node with the smallest index. So that means before I change my min-max distance, if they're the same, so if this max distance is the same as my current min-max distance, well then I don't necessarily change the min-max distance itself, but I might need to change the result. So the result will be equal to the smaller of the two. The result, the current node, or the current result. Okay, I think that's going to do it. Let's give this a shot. Okay, so it's passing our test cases. Let's submit this one and see how well it does. Whoa, and we actually pass. I am somewhat shocked. We actually passed, and we did pretty well. We beat 90% of other algorithms for runtime. We beat 40% for memory. Not too shabby. There's some things we can do to try to cut down on the memory usage. Like, I do have a bunch of these temporary variables. We could make we don't need n1, d1, n2, d2 because they're used in separate places. So we could just have node and distance. So they're shared. That cuts down on some memory use. We could do the same thing down here with like these temporary variables we're not really using. We can cut those out. It might come at the expense of runtime, however. So let's see, we have a couple minutes left on the Pomodoro. I'll take a quick stab at cutting these down a little bit. So this D1 and D2, let's cut this and put it in here. All right, so now we don't need these temporary variables. Let's get rid of these. That's going to help a little bit, maybe. Actually, we'll find out. So this D2 and node 2, so we could just say this is like N and D. Then I have to go through and like clean all these. Let's see. Okay, let's try this. I'm hoping I didn't make any mistakes. That still works. Let's see if we save anything on memory. Tiny bit, but it comes at the expense of runtime. So we were at 40% memory, but 90% runtime. We dropped down to 85% runtime and picked up 5% memory. I'd probably stick with the original solution given those two options. Go with the faster algorithm. I mean, 53 megabytes versus 52 megabytes, not a huge difference. Okay, I'll be posting this on my GitHub. You can check it out. Links are in the description. Hope you enjoyed this. Hope you had fun. Hope you learned something. And please write better code.